draw a free body diagram of all the forces acting on the ball. So of course there's going to be FG pointing straight down, and then there's going to be FN from the bowl onto the ball. That's going to be perpendicular to that point on the surface of the bowl, like that. Those are going to be the only two forces acting on the ball as it rolls inside the bowl. Part B, derive an expression for the magnitude of contact force exerted by the bowl onto the ball in terms of M, G, R, and D. So this will be our bowl. This distance will be called R. And then this will be the line from the center of the whole sphere to the ball. And that is also R, because this is supposed to be a sphere, and so the center of a sphere to any edge of a sphere will always be R no matter what. And so since this is a hemispherical bowl, then that also applies to this shape. So that's why these two distances will be the same. This will be the vertical distance from the center of the sphere to the ball, and this will be the horizontal distance from the center of the sphere to the ball. They make a right angle. This is called D, and the distance from the ball to the bottom of the bowl is Y, like that. Now, this is the ball right here, and of course, FG is right here. FN will be parallel to that line R right there. That will be labeled FN, and of course it will have components, one horizontal and one vertical, like that. And let's call this angle in here theta. That's a little theta right there. And so the vertical component of Fn and Fg have to be equal because they're the only forces acting in the y direction and they're pointing opposite ways. So Fn sine theta equals mg because this component of Fn is opposite the angle. And we also know that sine equals opposite over hypotenuse, and so in this triangle here, the opposite would be d and the hypotenuse would be r. So sine theta equals d over r, and then from here we can just make that substitution. So Fn d over r equals mg, and then from here we can just multiply both sides by r and divide both sides by d. So Fn equals mgr over d. Part C, prove that the tangential speed can be expressed as that thing. Okay, this one is a little bit of a doozy, but I will prove whatever I have been able to prove so far. So we start by analyzing our forces in the x direction, and that would simply just be our centripetal force, which will also be mv tan squared over r. Now, what is this r defined as? Well, this is the ball inside the bowl here, and it's tracing out a little circle here, right? Whatever the radius of that circle is will be our centripetal radius here, our little r. And so that would be this length of this triangle right here. And so we can make a truth statement. Little r equals big R cosine theta, because it's adjacent to the angle of this triangle here. And we know from part B that Fn sine theta equals mg, and so Fn equals mg over sine theta. We will use both of these. So centripetal force is defined as the net force pointing in the center of your circular motion, and literally the only horizontal force in this system is the horizontal component of Fn here. And so the mv tangent squared over r can be set equal to Fn cosine theta, like that. And now we can make this substitution in for the little r here, and this substitution for the Fn here. And so mv tangent squared over big R cosine theta equals mg cosine theta over sine theta. Again, we're just making these substitutions. The m's cancel. So we get this. And then we can multiply both sides by r cosine theta. The cosines will multiply together. And then finally, we can square root both sides. Now, we can use a trig identity here. Cosine squared plus sine squared equals 1. Therefore, cosine squared equals 1 minus sine squared. We can put that substitution into here. So we'll just put that here. 1 minus sine squared theta over sine theta. And then we know again from part B that sine theta equals d over r, so we can put that in the equation as well. Root rg 1 minus d over r squared over d over r, like that. And then in here we can just distribute the square, so it becomes g 1 minus d squared over r squared, like that, d over r. And then in this part of the expression, we can find a common denominator for this 1 and this d squared over r squared, which would be r squared. So rg times r squared minus d squared over r squared, like that, and then over d over r. Since we're dividing by a fraction, that's the same as multiplying by its reciprocal, and so we will multiply these two r's together and the d stays on the bottom. R squared g r squared minus d squared over r squared, and then over d. These r squareds will cancel, and so we get finally v tangent equals the square root of g times r squared minus d squared over d. Now, in the given prompt, the d is replaced with y here, and it looks like this. Now, our y is defined as the distance, the vertical distance from the ball to the bottom of the bowl. So the only way that these two can equal each other is if d equals y. And d can only equal y when the ball is halfway up the bowl here, right? Because if it's halfway up the bowl, then the distance above it and the distance below it will be the same vertically. So ball is halfway up the bowl. So I don't know exactly what is meant by y. I've seen multiple people try to prove that these two are the same, and I don't find their explanations to be satisfactory. They ended up assuming what they were trying to prove, and so this will be my answer. Again, d only equals to y if the ball is halfway up the bowl. The FRQ never tells us that until about part F, so don't really know what to do with that. But part D, derive an expression for the angular velocity in terms of big R and y and appropriate fundamental constants. Okay, so what we know is that little r equals big R cosine theta, and d equals big R minus y, right? Because big R would be this whole distance here. Subtract d from that distance and you get y, and that will be important later. And of course, we know that v equals r omega, and so omega equals v over r. So we can use our v tangent function that we found earlier, rg cosine squared theta over sine theta. And then since we want it in terms of big R and y, we will have to use this definition of our little r. And so we will have to multiply it by the reciprocal of this, because that's the same as dividing it by this. So 1 over big R cosine theta. Like that. And then we can simplify that further. This is the same thing as this. Right? If you square root this square root, I mean not square root, square it, then the square will distribute to this r and this cosine. And then if you square root that whole thing, then you get this original function. The only reason I'm putting the square root here is to put it inside this expression just to make it a little easier. So v tangent over r equals the square root of rg cosine squared theta over r squared cosine squared theta times sine theta. Like that. One r will cancel, and the cosine squareds will cancel. And so v tangent over r equals the square root of g over r sine, big R sine theta. Therefore, omega equals the square root of g over big R sine theta. And if we look at our diagram again, this is big R, and since it has components, then the sine of this angle here would be d, and so r sine theta would be d. So we can make that substitution, square root of g over d, like that, because again, opposite of the angle, so it's sine theta. And we know from here that d equals big R minus y, and so we can make that substitution. So omega equals the square root of g over big R minus y, like that. Part E, prove that the minimum value for the omega, which the ball can move in a circle, is square root of rg over r, big R. Okay, so we already know that omega equals the square root of g over d, right? Well, what is d? D is defined as the distance from the center of this sphere, or hemisphere, to the ball, right? And so, if we want to minimize the angular velocity, if we want to minimize omega here, because d is on the bottom of this fraction, we want to maximize d in order to minimize omega. And what's the biggest that this distance here from the top of the bowl to the ball could be? R. If the ball is at the bottom of the bowl, it can't go any lower. D cannot get any bigger. And so omega minimum will be the square root of g over big R, like that. And then we can split up that square root like this, and then rationalize it by multiplying it by square root of big R over square root of big R. And then we get square root of big RG over R. Part F, what is omega in revs per minute if big R is 20 centimeters and the ball is halfway up from the bottom of the bowl? So D will equal 0.1 meters, like that. Because 20 centimeters, I mean, half of that is 10 centimeters and then converts to meters. And so, again, we already know that omega equals the square root of g over d. And the distance from the center of the hemisphere or bowl to the ball, if the ball is halfway up, it will be the same as the distance up, and that is 10 centimeters. And so omega equals square root of 9.8 over 0.1 omega equals 9.899 rads per second, and we want to convert this to revs per minute, and so we divide it by 2 pi because that's how many revs there are in one, that's how many rads there are in one rev. Then we multiply that number by 60. So 9.899 divided by 2 pi rads in one rev equals 1.575. And then we multiply that by 60 seconds in a minute to get 94.533 revs per minute. Part G, derive an expression for the period in terms of the variables given and appropriate fundamental constants. Okay, so what do we know about the period? Well, we know that using angular velocity, the period equals 2 pi, which is the amount of rads in one rev, divided by the angular velocity, which is the rate of rads per second. And so if we multiply the number of rads by rads per second, the rads will cancel and we get seconds, which is time, which is our period. And so this equals 2 pi times our omega function, or the reciprocal of our omega function, which would be d over g, like that. And then again, d, as we clarified earlier, equals big R minus y. Again, right, this whole thing is big R. And so we can make that substitution. So t equals big R minus y over g. And yeah, that's the period. Part H, the ball is now rotating and we want to find the angular speed that the ball needs to keep it rotating with the ball stationary relative to the surface of the ball. Part H, the ball is now rotating and we want to find the angular speed needed to keep the ball rotating with the ball. So the ball will be stationary relative to the surface of the ball. Express the answer in terms of big R, G, and theta. Okay, so R, our ball here. Now what's different is that theta is now up here. This is still D, this is still Y. Okay. Now if we want to find omega, we need to focus on our forces acting in the X and Y directions. So FG, of course, will be this way. FN will be this way. Always has components in these kinds of problems. Angle will be up here. Okay. And so since the angle is up here, then the vertical component of Fn will be Fn cosine theta, and that will be equal to Fg, because the net force in the y direction equals 0. As for the x direction, it is simply our centripetal force, which is mv squared over little r here. Little r, of course, being this distance here. And we can turn that into mr omega squared because we want this in terms of omega. And that is because centripetal acceleration equals v squared over r, like F equals ma. And so take out the m and you get a. And then we know that v equals r omega. And so we can make that substitution. So r omega squared over r, distribute the square. 1 r will cancel. So centripetal acceleration equals r omega squared. And so we just combine that with m for our centripetal force. Now, we can take the tangent of the angle using the opposite, which would be the horizontal components, and the adjacent, which would be the vertical components. And so the opposite would be our sine theta, and so it would be this part right here, mr omega squared, because it's opposite the angle, because it's horizontal, right? And then divided by the vertical, which is the cosine, so mg, right? Because this is vertical, this is horizontal. We have m in both of these, and we want to cancel that out, just to make it easier to work things out, right? And so tangent theta equals r omega squared over g. Now, what is r? Little r specifically. Little r is big R sine theta, right? Because it's opposite of the angle. And so we can make that substitution. Big R sine theta times omega squared over g. Tangent can be rewritten as sine over cosine. Big R sine theta squared. Doing this because we want our answer in terms of big R, right? Sines cancel. And so we get 1 over cosine theta equals big R omega squared over g. And then we can simply multiply both sides by g and divide both sides by r. So g over big R cosine theta equals omega squared. Omega equals the square root of g over big R cosine theta.